Welcome to the session on integration, review exercises. The objectives for this session are to review previous topics through exercises, namely, differentiate functions using the chain rule, differentiate trigonometric functions, and differentiate exponentials and logarithms. We will also evaluate definite and indefinite integrals and find the area bounded by a curve and the x-axis. Finally, we will look at converting an expression with linear factors in the denominator into partial fractions. We will now solve the review exercises shown on your screen. Pause the video and have a go. When you are ready to view the solutions, press play. Before solving the first exercise, we're going to take a look at some theory which will help us to solve it. Composite functions, or functions of another function, can be differentiated using the chain rule. dy dx equals dy du times du dx, where y is a function of u and u is another function of x. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. In this example, given that y equals 3 minus 2x cubed, all raised to the power minus 5, find dy dx using the chain rule. So let's solve this. So we have this expression for y. And we let u equal the bit in the brackets, as shown here. So u equals 3 minus 2x cubed. We can differentiate this with respect to x to give du dx equals minus 6x squared. We can also rewrite y as y equals u to the power minus 5. And therefore dy du equals minus 5 times u to the power minus 6. We can now plug in du dx and dy du into the formula for the chain rule, as shown here. So we have this expression for dy dx. However, u is a variable which we have introduced, and therefore we must now replace it with the expression we originally had for u. So we have, tidying up, minus 5 times minus 6, which is 30, x squared, which stays as it is, and u becomes 3 minus 2x cubed. And of course, the u is raised to the power minus 6. And so we have our expression for dy dx. And now for the next exercise. We're going to find dy dx given that y equals 2 sin x plus 4 cos 5x. So let's solve this. We're going to differentiate each term separately. So for the first term, differentiating sin x gives us cos x, and therefore dy dx equals 2 cos x plus the differential of 4 cos 5x. And we work that out by applying k equals 5 to the formula for the differential of cos kx, as shown here, to give us the term 4 times minus 5 sin 5x as shown. And so tidying up gives us that dy dx equals 2 cos x minus 20 sin 5x. now for the next exercise. We are required to find dy dx given that y equals e to the power 5x plus 3 to the power 8x. So let's solve this. We can differentiate term by term, so let's consider the first term, e to the power 5x. If we substitute k equal to 5 in the formula as shown, we have that dy dx of this part of the expression is 5e to the power 5x, as shown. Let's now consider the second term for dy dx. If we plug in a equal to 3 to the power 8, as shown, we have that the second term differentiates to 3 to the power 8x times ln 3 to the power 8. And of course, ln 3 to the power 8 is 8 ln 3. And so we have our expression for dy dx. And now for the next exercise. So let's solve this. Before we begin, remember that when integrating polynomials, apply the rule for integration separately to each term. So, dy dx equals x to the 4 plus 3x squared minus 4x to the minus 3 over 2 implies y equals x to the 5 over 5 plus 3x cubed over 3 minus 1 minus 3 over 2 times 4 times x to the power minus 3 over 2 plus 1 plus c, which tidies to x to the 5 over 5 plus x cubed plus a half times x to the power minus a half plus c. The rule for integrating kx to the power n is that if f dash of x equals k times x to the power n, then f of x equals k over n plus 1 times x to the power n plus 1 plus c, where n does not equal minus 1. When integrating polynomials, apply the rule for integration separately to each term. Let's now take a look at definite integrals. If f dash of x is the derivative of f of x for all x in the interval ab, then the definite integral is defined as integral from a to b f dash of x dx equals f of x between the limits b and a, which equals f of b minus f of a. An integral between two limits can be calculated and is called a definite integral. Recall that an indefinite integral produces a function, and a definite integral usually produces a value. Let's now take a look at the steps for integrating definite integrals. First, write the definite integral statement with its limits. So, for example, integral from a to b f dash of x. Then integrate and write the integral in square brackets. So, f of x is between square brackets between the limits b and a. Evaluate the integral by working out f of b minus f of a. Let's now take a look at an example. Let f dash of x equal 4x cubed. We will find the integral of this function between limits x equals 2 and x equals 5. Now the integral from 2 to 5 of 4x cubed dx here from x equals 2 to x equals 5 gives us x to the 4 between the limits 5 and 2, as shown. And this is equal to 5 to the 4 minus 2 to the 4. And working this out gives us 625 minus 16, which equals 609. Now the area between a positive curve, the x-axis, and lines x equals a and x equals b is area equals integral from a to b y dx, where y equals f of x is the equation of the curve. So diagrammatically it will look something like this. We've got a positive curve, f of x, and we've got limits a and b, and we've got the shaded area in yellow beneath the curve. Let's take a look at an example. Find the area of the finite region between the x-axis and the curve y equals 15 minus 2x minus x squared. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. If we factorize this function, we obtain 3 minus x times x plus 5. The intercept with the y-axis is 15, and the curve crosses the x-axis at x equals 3 and x equals minus 5. Therefore, if we're wanting to find the finite region between the x-axis and the curve, we're looking for the region between minus 5 and 3, which is below this curve. So area equals the integral from minus 5 to 3 of 15 minus 2x minus x squared dx. And so integrating this term by term, we obtain 15x minus x squared minus x cubed over 3. And then putting in the limits, so x equals 3 here, and x equals minus 5 here. And then tidying up, gives us 8 1/3. Before moving on to the last exercise, we're going to look again at some theory. A single fraction with two distinct linear factors in the denominator can be split into two fractions. This process is called splitting into partial fractions. So, for example, 3 over x plus 7 times x minus 5 is identical to a over x plus 7 plus b over x minus 5, where a and b are constants. So notice that we have rewritten the expression on the left as the sum of partial fractions. There are two methods of finding constants a and b. either substitution or equating coefficients. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. We are required to split the expression shown on your screen into partial fractions by substitution. So let's solve this. We let the expression equal or be identical to a over x plus 3 plus b over x minus 2. We then add the fractions on the right-hand side by putting them over a common denominator as shown. Therefore, we now have that the numerator on the left-hand side is identical to the numerator on the right-hand side. If we let x equal 2, and we do this in order to get rid of the a term, we obtain 5 times 3 on the left-hand side, and a times 0, this was what we were trying to do, get rid of the a. So a times 0 plus b times 5 on the right-hand side. This gives us b equals 3. Now if we let x equal minus 3, we have 5 times minus 2 on the left-hand side, and a times minus 5 on the right plus b times 0. And of course this is why we put x equal to minus 3, so that we could get rid of the b and find a. And so tidying up gives us that a equals 2. So we've found the values of a and b. And we can express our fraction as 2 over x plus 3 plus 3 over x minus 2. And now for part B. We are required to split the expression shown on your screen into partial fractions by equating coefficients. So let's express this as a over x plus 3 plus b over x minus 2 as shown. And then, similar to the previous part, we express this as a single numerator over a single denominator. And again, we have a similar expression as previously. Now let's multiply out. So on the left-hand side we have 5x plus 5, and on the right-hand side, if we multiply and tidy up, we have ax plus bx, we've put the x's together, plus 3b minus 2a. We've put the constants together. In other words, a plus b times x plus 3b minus 2a. So equating the coefficients of x, we have 5 equals a plus b, and equating the constant terms, we have 5 equals 3b minus 2a. Here are the coefficients of x. and here are the constant terms. We're going to call these equations 1 and 2. Solving by multiplying the first equation by 3 and then subtracting the second equation gives us 10 equals 5a. And this gives us a equals 2. We can substitute a equals 2 back into equation 1 to give 5 equals 2 plus b. And rearranging this gives us that b equals 3. So a equals 2 and b equals 3. This brings us to the end of this session. If you have understood its contents, you should be able to differentiate functions using the chain rule, differentiate trigonometric functions, and differentiate exponentials and logarithms. You should also be able to evaluate definite and indefinite integrals, as well as find the area bounded by a curve and the x-axis. And finally, you should also be able to convert an expression with linear factors in the denominator into partial fractions. Thank you very much for listening.